Okay, so just the first one. I'm not sure where you want to start.
Sure, I'll have to get it up on my computer. SHW 5.
Yeah. Explain why a storm cloud before a lightning strike is like a giant capacitor.
Because it's holding a lot of energy. I didn't think you could store energy, but then yesterday in lecture you said you could store energy.
Yeah, a capacitor storing energy in the form of either a charge separation or an electric field. So when you have a storm cloud, remember we talked about that in that first lab. You have the storm cloud, and what happens in the cloud?
Does it polarize?
You have ice crystals that fall down, or actually, so ice falls down, that's water that falls down, I don't know. And the interaction between the water and the ice, the rubbing as it falls, causes it to charge up, just like when you rub the amber rod with fur. And so you end up with the cloud having a charge separation. So the bottom of the cloud is, if I remember right, positive, and the top of the cloud is negative. Now, that's just my recollection. Let me actually make sure that I'm correct about the...
I think I have. We wrote down the picture. I think we turned it in, though. We took notes from that lab.
Yeah, but they're returned to you.
Yeah?
Yeah, on Moodle.
Oh, okay. Gotcha.
So, yeah. Yeah, that was correct. So you have a charge separation there in the cloud. And so how is that like a giant capacitor?
Because it has two parallel rods.
Yeah, it's behaving almost like you have two parallel plates. Like you have one plate down here that has plus Q, and one plate up on the top that has minus Q. So that's kind of like a capacitor.
Yeah.
And of course, there's electric field. What direction is the electric field going to be in this case?
It's going to be up.
Because it goes out of positive and into negative. Yes, it is cool.
I don't know what they'll want for me to put in the actual answer, but I'll figure it out.
Well, you just explained just like I did. So you definitely draw a picture. And
I can draw a picture on the application though.
in the application,
yeah.
No, you can't.
Yeah, I was just I don't know what they want for that entry, in the application, but that's fine.
Well, let's look at what the options were for answers. It's just looking for you to describe it, and then you have, as it contains a high amount of excess charge, is their answer. It has a charge separation. Yeah, I would not have gone with their answer. I would have gone with my own, right? They say that the cloud has a high amount of excess charge. Well, a capacitor doesn't have a large amount of excess charge. It has a separation of charge. Okay. I'm not going to argue with them.
Calculate the equivalent capacitance from points A to B using the figure if each capacitor has a capacitance of 1 microfarads.
Right.
Okay. So
what's your key idea here?
capacitance or
It is capacitance, but
circuits like using parallel or series.
okay, now we're getting there. We're going to do adding capacitors. Capacitors in series and parallel. So the first question you have to ask yourself, I'm not going to quote Dirty Harry here, is do you see anything that's in series or parallel?
Yes.
What do you see?
I see. So from the diagonal from A to B is in parallel
With
itself, or like from.
You can't be in parallel with yourself. You just are yourself.
Okay. I don't know. It's kind of standalone. Everything else is in series.
Okay. What you have is two pairs of capacitors that are in series. So I've circled them in red. So let's combine those first.
Yeah, you would add them, and then all of them were in parallel.
I'm back from Girls' do you mind if I borrow your keys to open the microbiology lab? Sorry to interrupt you.
It's okay. And what's your name?
Kayla.
Okay. That way, if he asks,
Thank you.
Yeah. Okay, so we need to add two capacitors in series. So how do you add capacitors in series?
Just add them. Like, wait, is it resistors that you add?
It's resistors.
So capacitors in series is 1 over. I always get those confused.
Wow, capacitors. So 1 over, and I'm going to put C2 since it's two capacitors. It's equal to 1 over C plus 1 over C. Well, what's 1 over C plus 1 over C?
C? No.
Thank you.
You're welcome. I have 1 over C and 1 over C. They're exactly the same thing.
1 over C.
No. A plus A is not A. What's A plus A?
A2. Or like
2A.
2A, yeah.
So what's 1 over C plus 1 over C?
2C.
2 over C.
Yeah.
So that's
okay, yeah.
2 over C. So that means that if we invert everything, we'd have C2 is equal to C over 2. Okay, so now we have this is C over 2, this is C over 2, and that's C. So I'm going to redraw my circuit, and I'm going to keep my A and B the same place just to make it look similar.
Okay.
And I have C here. C over 2 there. C over 2 there. So actually this middle one was a little, let's make it centered. So the middle one has remained unchanged, but I replaced each pair that was in series with an equivalent. Now what kind of relationship do I have between the capacitors we see now?
Now they're all in parallel.
So now they're in parallel.
Or 1 over.
I was listening to one of my lectures yesterday. I noticed when I'm writing, it's very quiet. Okay, so we're going to add 3 capacitors in parallel. So how do capacitors in parallel act? Or add?
1 over.
No, that was in series.
Oh. What? In series?
In series, it was the inverse.
Oh, because I'm...
Yeah, we have to get the resistors and capacitors separate. That's the whole reason for these kinds of questions, make sure we have that straight.
Okay, so you just add them like normal.
Okay, so we're going to have C parallel is equal to C over 2 plus C over 2. What do we get when we add those together?
C 3 over 4.
Let's start with the easy. What's C over 2 plus C over 2?
And C over 4. C over 2.
What's 1/2 plus 1/2?
1.
1. Okay, so C over 2 plus C over 2 is
2C.
C times parentheses 1/2 plus 1/2.
So 2C.
So it's C, and then we add C. So the total is 2C, which of course they told us microfarad. C is 1 microfarad, so it's 2 microfarads. So the point that we need to learn here is how to add capacitors in series and in parallel.
Yeah, because capacitors in series they add 1 over, but the resistors add just normal.
Yes.
Whereas in parallel, your capacitors add normally, and then your resistors add like in fractions.
Well,
1 over.
inverses.
Yeah.
Yes.
Okay.
Okay. Go on to the next one.
Yeah, I think we should just do the first 3 because it says that after that they're just practice problems of what SHW.
That's true. Okay, so this one. A large laser used to ignite a fusion reaction, such as the National Ignition Facility, NIF, requires short pulses of energy. The laser is in this huge building. I think it is the world's biggest laser, the one there at NIF. At least it was when I was there. I was there. Well, actually, when I was there, it was only half working. They only had half of the laser beam running yet. The other half was still being set up. The energy is supplied by capacitors stored in large rooms. The total capacitance is 6.2 times 10 to the minus 2 farads when a voltage of 10 kilovolts is applied across all the capacitors. These capacitors produce 5 nanosecond pulses of energy and are charged with a 2 kilowatt generator. What energy is stored in the capacitors? Okay, so we've got to our first question. What energy is stored? So we need to know what is the equation for potential energy on a capacitor.
Is it 1/2 V squared C squared? That's equal to the PE. At least what I have.
There should only be one square in there.
Is that the right equation?
It's the one we're looking for, but you somehow have it written down wrong.
That's not good.
So the equation is 1/2 CV squared, which if you use the relationship between Q and V and C, you can write it 2 other ways as well.
I have 1/2 CV squared over AD.
Those are the 3 ways that you can write it.
Okay.
So which one of those three is the one that's going to work for us? We're given C and V.
So just the first one?
The first one, right? So we'll have potential energy is 1/2 our capacitance, 6.2 times 10 to the minus 2. I forgot to write farads there. Times the voltage, 10,000 volts squared. And so 10,000 squared is 100 million, or 10 to the 8th. 10 to the 8th times 10 to the minus 2 is 10 to the 6th. And finally, we have divided by 6.2 divided by 2, which is 3.1.
Yep.
Okay, so we have the potential energy stored. Because a capacitor stores energy in the form of either a charge separation or an electric field. Yeah, getting that. Okay, so that's how much energy is stored. That's part A. And then part B says what power is produced when the capacitor is discharged. So we're going to have, this is our time. What is power?
Power is like, I was just using it yesterday.
You were, but just think about what power is, not the equation you were using yesterday. The equation you were using yesterday was VI, which isn't going to help us with this.
Power is like the energy, or like Q times.
Think back first semester. What is power?
Power is like work times distance.
No. It's you're thinking in the right arena. Power is the rate at which work is done, or the rate at which energy is converted. It's a rate.
Okay.
What does that mean if it's a rate?
It's like a ratio? Or
It's a ratio of what to what?
of time to like energy put in.
Okay, it's energy per time. So it's the rate of energy transfer. It's the energy per time. And so the energy transfer, we're going to have all of this energy from the capacitor transferred. So our energy transfer is going to be the potential energy divided by that time of 5.0 nanoseconds.
Okay.
Whoops, I should have waited to the next one to put in a number. So that's 3.1 times 10 to the 6 joules divided by 5 times 10 to the minus 9 seconds. Now, if I'm dividing by 5, then if I multiply top and bottom by 2, that would be 6.2 over 10, or 0.62. And then I have, or let's just make it 6.2 times 10 to the 5. And then 5 plus 9 is 14. Joules per second, which is watts. Now, what's key here? We're charging it with a 2 kilowatt generator. That's 2 times 10 to the third. We're getting out 6.2 times 10 to the 14th watts. Third versus 14.
Yeah.
Why do they use the capacitor?
Because it stores energy. Because it like let us get more energy out.
Because it let us dump the energy quicker.
Okay.
During that 5
rate.
nanoseconds, it's using more power than the rest of the city.
Nice.
You know, so they couldn't just use the municipal power supply, or else they'd have to black out the city and then some. So they charge over time. So that's our last part. How long does it take to build up this amount of energy? So we have now power charging is equal to change in energy over delta time charging, right? The one above was discharge. I didn't put discharge because I didn't realize we were going to do it both ways. So we're looking for the change in time discharging. So what's our equation for change in time discharging going to be? Very simple.
Like 1 minus initial?
Well, from this equation, we should be able to solve for the change in time charging.
Gotcha. So we would have like change in time equals power times, or no, be power divided by something.
Well, we need to multiply by delta TC and divide by PC. So it will be the energy change over the power charging.
Okay.
So that's going to be our potential energy over the power charging, which is 3.1 times 10 to the 6th joules divided by 2 times 10 to the 3rd watts. 3.1 divided by 2 would be 1.55. And then 6 minus 3 is 3. So it takes 1,550 seconds. Usually we want to get that into something that is going to be meaningful to us in minutes and seconds or hours, as the case may be. So we'll take 1,000, it's actually going to be minutes, 550 seconds times 1 minute per 60 seconds is equal to 155 divided by 6. 6 goes to 15 twice, 35. What's my next digit? Say repeating now. You put your numbers in the wrong order. I was like, that's not right. I think it's 8 gives me 48, 20. Is that it?
Did you convert again? Because
okay, your numbers, that's seconds, so it's 1550 divided by 60.
Yeah.
You have 15505. Which I know you saw my S's.
Yeah, yep.
8-3, okay, not 2-3.
I guess I thought your S was a 5.
So it takes almost a half hour, 25.83 minutes to charge, and it takes 5 billionths of a second to discharge.
What do they use that for?
That's where we started. It's for igniting fusion reaction. What they have is they have a little capsule, and then there were different designs, and of course designs could have changed since I was there, but they had laser beam that was coming in and focusing on the capsule, and I think it was supposed to have laser coming in on both sides, but when I was there it was just one. I could be wrong on that. And so that laser beam is bringing in a huge amount of energy, right? All of this energy, 3.1 million joules or 3.1 megajoules into this little capsule. And so all of that energy is going to heat it up to an incredibly high temperature. And so in that capsule, they have, I think it's deuterated. Well, it's deuterium and hydrogen mixed together. And so you have deuterium, of course, is a proton, neutron, hydrogen, just protons. And with this much energy, they're going really fast. And since they're going really fast, they'll have enough energy that they will be able to overcome the Coulombic barrier, the force of repulsion between charges, and get the nuclei close enough for the strong nuclear force to interact and then they can make them stick together, fuse, and form helium. And so that's what they're doing, is they're taking hydrogen and causing fusion to make helium. Now, the process of fusing into helium releases more energy than it took to make them come together. The goal of the experiment is, of course, to reach the point where they can have, and I believe they have reached break even. That is, the amount of energy they get out is more than the energy that was in the laser pulse, right? Because as soon as you reach that point of having more energy out than energy in, now you have something that potentially could be used for providing power. And we have the water is filled with just taking the top inch of the oceans to supply us power for centuries. Taking the deuterium from the top inch of the ocean. So that's what their goal is ultimately. Now, there's big problems besides just reaching break even, because this, well, first of all, it takes almost a half hour to recharge. So you don't have boom, 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 boom. You don't have a continuous source of energy. You just have a pulse of energy. And so you want to try to make it so you can have something more continuous. And their chamber, they have to wait for everything to be settled down, take this out, put a new one in. So there are other people who are working on ways to try to make this so you could make it a repeat. One of the things they talked about when we were there, and I was there, actually it was right before I came here, was the last time I was there. So it was 16 years ago. And they were saying one of the ideas that they were experimenting with was seeing if they could drop a droplet and then time it so when the droplet's at the center, then the laser beams fire. Everything happens without it being in the chamber here. Now, these chambers are very carefully designed, so they have reflectors and stuff to concentrate that laser energy and not have it going out. So this would take away the reflectors. It'd be a little more of a challenge, but then you'd have something that could be kind of continuous, like very quick, boom, 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 if you could overcome that 25.83 minute barrier to doing it.
It's still impressive, but yeah, I can see how that could be a problem if you wanted it to be a power source.
Well, I mean, that facility is very, very impressive. It's their second one. They had the Nova first, and then they built a bigger one. So I toured the Nova before NIF was built, and then.
Where is that?
This one here is in. It's in the Stanford area. I'm trying to remember. I think it's Lawrence Livermore Lab. It's somewhere in the Bay Area. I really should know.
You're fine. I was just interested. That's cool. Can we do SHW number 6? Or like SHW 6?
Yes.
That's really cool. I have to look that up.
Yeah, I've actually toured, since I've toured both NOVA and NIF, I also toured an inertial confinement lab in Japan. So I've toured 3 different ones,
wow,
which I think is pretty cool.
That is pretty cool. Why'd you go to Japan? Just for fun?
I was there in a research thing.
Wow. I want to go places for research things.
Yes, where they pay you to go. So much better when they pay you to go.
Yes.
Yes, so I was paid to go to Japan. They gave me money so I could afford to go see different facilities. It was very awesome.
Wow. Yeah.
Okay, a defibrillator sends a 6 amp current through the chest of a patient by applying 10,000 volt potential as in the figure below. Boom, 10,000 volts, 6 amps. What's the resistance?
Well, so can I use V equals?
I'm actually going to remove this and do this in a more organized fashion. Oops.
mean, I have V equals K times Q divided by R, but I don't think that's resistance yet.
Okay, it's a very simple relationship. We have Ohm's law. V is equal to IR,
Okay.
right? Or R is equal to V over I.
Gotcha.
Now, this equation only works if you have a resistive material, but since they ask for resistance, that implies that it's resistive. There's some materials that follow different relationships. Actually, I think they call these ohmic materials that obey Ohm's law. And so we just have to put in the voltage. So what was the voltage here?
6.
10,000.
Oh, gotcha. Yeah.
10,000 volts, that's the electric potential, divided by the current, which is where you had your 6.
Mm-hmm.
So 10 over 6 is 1 2/3. So 1, 6, 6, 6, repeat. Well, let's put 1, 6, 6, 7.
Yeah, this is.
Okay, so that's our resistance.
Cool.
All right, why do we have this? Well, just something to remind us of what's going on when we use that defibrillator. Notice the picture shows a capacitor. You charge the capacitor, just like in the previous problem,
Mm-hmm.
and then you dump that energy through the chest. Now, we talked about the RC time constant. And so you need to have a fairly short time for dumping that energy. And this is a reasonably large resistor, so the capacitor is going to have to be reasonably small
Mm-hmm.
to allow you to dump that energy quickly. And so you can go through and you calculate, okay, so how much time do we need to have? And you can go through and calculate what capacitor you're going to need to, and what volt, well, how much energy. It's all calculation we can do. We would need at least a parameter on how much time before we could go any further.
Okay. Mm-hmm. The following curve shows the voltage as a function of current in a circuit over approximately what range of voltage is the circuit on?
Yeah, remember I just used that word?
Mm-hmm.
Okay, so how do you answer? What does it mean to be ohmic?
To have the same relationship as Ohm's law.
Yeah. So V equals IR. What should V equals IR look like?
It should be a straight line.
Okay. So I tried to draw a straight line. Apparently it didn't recognize that as a straight line. Still not recognized as a straight line, but we're just going to pretend that it was because it looks pretty good to me.
Okay.
So I drew a straight line because that's what Ohm's law says.
Yeah.
And so over what range of currents does the actual...
Like from 0 to 3.1 maybe?
Okay. So that would be a reasonable answer. Something like out to here.
Mm-hmm.
Because my line wasn't perfect, but you can start to see it deviating away there. So that would be a good answer, 0.1. And that's the one they chose.
If the 0.1 millimeter diameter tungsten filament in a light bulb is to have a resistance of 0.2 ohms at 20 degrees Celsius, how long should it be?
Okay. Any idea how we're doing this? That's right. We're going to have resistance is equal to the resistivity times the length divided by the area. And so they gave us the diameter. What use is the diameter going to give us?
For length.
Area
Okay.
is pi r squared, or pi over 4 diameter squared. So we have the information we need for the area, and we have the resistance. So we're given that R is equal to 0.200 ohms. And then we have a temperature.
Yeah, because temperature, something about, I forget the relationship it has, but it affects the resistance.
Okay, so what we're missing is what is rho, because we're looking for L. We need to find rho. And so that's something we have to look up for tungsten at 20.0 degrees Celsius, because it'll be different temperatures.
Then would you use this equation instead?
If they gave you rho at like 0 degrees Celsius, yes, but you'll probably find rho at 20 degrees, and then you don't need that. So it's resistivity of tungsten.
Got it. It's 5.6 times 10 to the -8.
At what temperature?
Oh. At 20 degrees Celsius.
Really? Because this says it's 52.8 ohm meters at 20 degrees Celsius.
Why? Where's in the book? I just went to the section they had. It could be wrong.
Well, I'm a little confused because I have two different sources here, both from hyperphysics, and they seem to say different numbers. Resistivity at 20 degrees Celsius for tungsten is 5.60 times 10 to the minus 8. Okay, so that's what you said. Ohms times meters. And so now we can put it all together. Now it's just math. L is equal to resistance times area over rho is equal to 0.200 ohms times pi over 4 times diameter was 1.00 times 10 to the minus 4 meters quantity squared. So there's our, there's how you can't see it there. There's our equation, and we just have to put that in the calculator.
Yeah, we've done the physics part. It's okay.
Yeah. Yes, we have. We've done the physics part.
It gives me an excuse to like check back on it later and look at it again. So.
Okay, do the next one here.
Mm-hmm.
Electric power. Circuit consists of a 12-volt battery connected in parallel with 3 other parallel branches. So what was that circuit going to look like? Here, just draw it.
In parallel. That's a very straight line. Something like that, I think.
Okay, that's correct. So we have 12-volt battery. Each of the other parallel branches contain 2 resistors connected in series. So each branch has 2 resistors, not 1. So we have to replace that. So we have 2 resistors, and each resistor is 30 ohms. So each one is exactly the same. And it asks us for how much power is dissipated by the middle branch.
Divide by that. Like, if they are all like giving off the same amount, all of them are parallel to each other.
Mhm.
So you just like add them all up and then divide by like, that circle, like those two.
It's easier. Right. A problem like this is mostly given for you to realize the simplicity. You have, these are in parallel, right?
Mm-hmm.
If they're in parallel, what's the same?
Capacitance?
Well, they're resistors.
So the resistivity of them? Sure.
Well, anything in parallel in a circuit, if things are in parallel, they have this the same. If they're in series, they have this the same.
I just remember that they added, like, parallel is usually 1 over.
That's how you add resistors, but I'm not talking about how you add resistors. I'm saying what's the same for different elements if they're all in parallel.
I'm sure.
Okay, what's the same is their voltage, because see,
Okay.
the 12 volts, this is going to be plus 12 here, 0, plus 12, 0, plus 12, 0, because this here is all connected to the negative side. I'm calling this 0. That means that in my head I put a ground connector there, so that's my reference. Sometimes we put it in a parenthesis, meaning it's not really connected to ground, but I'm considering it ground. And so these are all plus 12, so the voltage drop across each one of these is the same. It does not matter what I have here. Those resistors could be completely different. It doesn't change my problem in one bit. I mean, unless you're drawing more than the battery can supply, but we don't have any limit for the battery, so we assume that. So all we have to do is in our head say, well, let's just look at, it's a battery, so we should put a battery instead of a cell. There's the one we care about. I just took out the others because they don't change what happens here. And so this is 12 volts. This is 30 ohms and 30 ohms. So what's the total resistance?
60.
60. So this is equivalent to and so I ask, what's the power there? So we go back to where we started today. What were the equations for power? You got them right there.
P equals I squared times R.
Okay, that's one of the three. I squared times R.
RP equals I times V.
Okay, or
RP equals V squared over R.
so what do I have already? What 2 values do I have?
You have the voltage.
Okay, so that means that I'm going to narrow it to these 2 because those both have voltage.
Mm-hmm.
And
you have R.
And so that means I'm going to narrow it to these 2 that have R. Well, the only one that's in both of them is that one.
Mm-hmm.
So I'm just going to say my power is equal to V squared over R, is equal to 12 volts quantity squared over 60 ohms is equal to 12 squared is 144 volts squared over 60 ohms. And so then you just have to take, and what would have been easier would be for me to say 12 times 12. 12 divided by 6 is 2. 2 times 12 is 24. $2.4 watts? No, it's not 2.4. Yeah. Yeah, it is.
Yeah.
So this problem here, it was very simple to solve.
Mm-hmm.
The key was just thinking about what does it mean when they're parallel?
Could I ask you one homework problem with our chapter?
Sure. Which one?
I wanted to just put A1. Are you still recording?
Yes. All right, so let's copy this one. Wrong thing.
Wait, is this? I think this is the same as what we did earlier. The time equation.
Okay, well, it's not exactly the same. In fact, it's not at all the same.
Oh, okay.
Okay, so we have a situation where we have two capacitors, a 3 coulomb and a 5, or 3C and 5C, where C is 0.14 farads, are connected in series with resistor 5.5. How long will it take for the amount of charge in the circuit to drop by 75%? So we don't know what the charge is. We just know that it's going to drop. So the first question we have to ask ourselves is, how is time going to relate to charge? How is charge going to vary with time?
It's the rate, right? Or like power?
Well, we have from class yesterday, we saw that voltage is going to be for discharging the voltage peak times e to the minus t over tau. That was our equation for how the voltage is going to change when it's discharging. What is tau in this equation?
Time. That's
T is time. What is tau?
like the percentage.
No, tau is what we call the RC time constant.
Oh.
Now, in this case, our C is a little more complicated because they gave us C, but C is not the value of the total capacitance. C is just something they're using to find. Sorry. Total capacitance.
Bless you.
So we're going to need to find the RC time constant first.
Okay.
But this is voltage, it's not charge. How does charge relate to voltage?
Voltage is charge divided by
Right. Q is V equals VC, so V is equal to Q over C. Sorry.
It's okay.
Okay. So Q is VC.
Mhm.
C is a constant, so we'll be able to just take this and say Q is equal to the Q we start with, e to the minus T over tau, just by using this relationship that the charge is proportional to the voltage. Or if you wanted to see it more explicitly. Come on. Something's not updating. There we go. So we are given a situation where we know that Q is equal to, it's dropping by 75%. So if it drops by 75%, what is Q going to be compared to Q initial?
75% less.
75% less, which is what value? If I start with $100 and I lose 75% of my money, how much do I have left?
29. Right. $25.
Yeah. So that means I'm going to have 0.25 Q initial is what I'm left with. And that's going to be equal to Q initial e to the minus T over tau. Well, I can just look at the two things on the right. Let me change the color for the two things on the right so we see what I'm working with here. And I can say that means, just going to erase that to make it look better, that I could cancel the Q aughts in those, and I would have 0.25 equals e to the minus T over tau. How do I find time given that equation?
You need to bring, isolate T, so you take the square root.
No, this is an exponential, and so I'm going to have to use the inverse function of the exponential. So I'm going to actually separate things here. Move this over here, and I'm going to do natural log of this equals natural log of this. So I did the same thing on both sides. So, if it's 5 equals 5, natural log of 5 has to equal natural log of 5. And the right-hand side simplifies because they're inverse functions. So that's just minus T over tau is equal to the natural log. And I'm going to put 1 over 4 because it's more fun to write than 0.25.
Okay.
And so that means that tau is equal to minus T over the natural log of 1/4. Or I wasn't solving for tau, I was solving for T. My mistake. Solving for the wrong thing. Then T is equal to minus tau natural log of 1/4. Now, just a fun trick to make life easier. Natural log of 1/4 is minus natural log of 4. So it's equal to tau natural log of 4. So that's going to be my answer. But what am I missing?
The percentage?
No, I'm missing tau. What is tau? Well, that's where we started. It's the RC time constant.
Mm-hmm.
And so for the RC time constant, I have the R right there, but I need to find the equivalent capacitance for both of these because both of those are my capacitor. So those are series. What's the equation for finding C series?
Do you add them like normal, or is it the reciprocal?
It's reciprocal. So it's going to be 1 over 1 over 3c plus 1 over 5c. And of course, I'm going to want a common denominator there, so I'm going to multiply everything by 15c, top and bottom.
Mhm.
So I have 15c over would be 5 plus 3. So 15c over 8. And you are given that C is 0.14 farads. So there's your C value. Or I said you are. I was given this. And so since these are my numbers, let us calculate this. What's 15 times 0.14 divided by 8? Okay, so 0.2625. And so that means tau is equal to RC. The R I'm given is 5.5 ohms times 0.2625 farads. So what's this times 5.5?
1.4.
1.44. I'll put 375, even though clearly we don't have anything close to that number of sig figs. We only have 2 sig figs. So 1.4 would be enough for, And then we need to take that and multiply it by the natural log of 4. And so that's 2.001 seconds. So let's check and see if we did the math right. 2.00. They had 1.992. Somewhere along the way, we made a mistake somewhere. It gave it to me as right, but that's a pretty, 1.992, 2.00. They could have dropped a digit somewhere because it's actually, in the 4th decimal place. Right? It's 9 in the 4th decimal place, but it's in the 4th decimal place. Okay, yes, it is time for chocolate.
Sounds good. Thank you.
Yep.
Yeah.